Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture of this course on control systems. And in the last lecture, let me refresh your memory a bit. In the last lecture we have discussed about these different types of steady state errors given that the test signals are of three specific types: the step, the ramp or the parabola. And we have derived these expressions for the steady state error, that is the ES in the block diagram. The thing that I must repeat again is that remember that this error that we have defined is only with respect to this unity feedback structure, okay. So if it is a non-unity feedback structure, in other words, if there is a non-unity term in the feedback loop, okay, in the feedback path, then you must convert it to its equivalent unity feedback form and then talk about this error. Otherwise the error that we will be talking about is not the error that we are concerned with, rather it will be the actuating error, okay. So that is a point that is to be kept in mind. Now, as I promised in the previous lecture, you see before yourself on the screen that we have now tabulated the different types of errors according to the type of a system. And as you can see, the definition of the type of a system, as we discussed again in the previous class, is given on the top of the slide, which is the number of poles of a system at the origin defines its type. Standing assumption for all of this is that the final value theorem is applicable, which is another way of saying that the system is closed loop stable. Only then all of this makes sense. So quickly let us go over that table again to jog your memory a bit. We saw that if you have a step input and a type 0 plant, then you have a constant steady state error. If you have a type 1 plant with a step input, you will have 0 steady state error. If you have type 2 or higher, or any other type for that matter, rather than type 0 in fact, then you will actually have 0 steady state error, okay, with a step input. With a ramp input, of course, with type 0 system, you will see that the steady state error will be infinity. If I can just sketch it, it will look something like this. So for example, if you have your ramp input, it will look something like this, a straight line with a constant slope, and your response you will see will dither from it, okay. So as this time increases, you will see that this difference between the input and the output keeps getting larger and larger, okay. So that is basically an infinite steady state error, alright. On the other hand, for a ramp input, if you have a type 1 system as opposed to for a step input, here instead of 0 steady state input steady state error, you will actually have a constant steady state error. So the sketch of that constant steady state error would look something like this. So for instance, if this is your ramp, right, now for a constant steady state error, your output would look something like this. So it is going to be like shadowing this. So this value is a constant, okay. As t goes to infinity, this constant value, this constant difference is held, okay. Similarly, now if you increase the type to type 2, that is 2 poles at the origin, and if you have a ramp input, you will see that the steady state error eventually goes to 0, in which case the sketch would look something like this. So for example, if the black line again as before denotes your input, okay, then the output will eventually catch up with the input and there will be 0 steady state error. So this black and the red lines will merge together, alright. So that is an illustration of what happens for different types of systems subjected to a ramp input in an unity feedback closed loop configuration. Similarly, by the same token, for a parabolic input, you will see that for a type 0 system, again the steady state error is going to be infinity. For a type 1 system also, the steady state error is going to be infinity. For a type 2 system, you are going to have a constant steady state error, and for higher than type 2, only then a parabolic input will lead to 0 steady state error. Okay. So these are all expressions we have derived, most of them. If some of them are remaining, you can take it up as an exercise to fill up the gap in this array. So you see we have derived Kp and side by side the error due to this step input for a type 0. Similarly, Kp and this error for type 1, Kp error for type 2, so on and so forth. So once you derive one of these expressions, the other one follows straight away. Okay, you should be immediately able to do this. Okay, so that kind of summarizes what we've done till the last lecture, where we talked about these steady state errors. Now these steady state errors have a lot of applications in some very practical systems, and a lot of studies have been conducted even up to, let's say, 15 to 20 years back, okay, where people were still designing suitable controllers for this steady state error which they wanted to control and make it 0, and for rejecting things like load disturbances. So for some very specific kind of class of systems, maybe time delay systems or complicated class of systems. Okay. Now before we get into that, let's just quickly go over a couple of things here. So these are some insights that we often might overlook. Now suppose in a question or in a problem someone tells you that, so here's the question. So suppose someone tells you one of the error constants. So it could be the position error, the velocity error, or the acceleration error. Okay, and it is finite or non-zero. Okay. So suppose I tell you the value of, let's say, Kp or a Kv or a Ka for a particular system, and I give you a number that it's 0.5 or it's 100 or it's 250, something like that. I just give you a number, or maybe something finite, something non-zero, any number I give you. The question is, apart from this number, what else can you infer about the system apart from this number? Okay, so that's an interesting question. So let's think about it. Let's take it up piece by piece. So if someone has been able to evaluate this error constant, yeah, that means someone has been able to apply the final value theorem to what? To the sensitivity function, apparently, right? Otherwise, of course, you can always apply this final value theorem. You can always find out limit s tending to 0, s, gs, and so on. But then, it doesn't make sense, right? If I'm giving you this value, it means that I want you to use it for some reason, right? So if I'm just giving you this value and I can always evaluate this, but this doesn't make sense until it is applicable. So if someone is giving me this value with the hope that I will be able to use it, then one of the things that I will immediately deduce is that the system is at least closed loop stable. Otherwise, what good is this value to me? If the system is not closed loop stable, then there's nothing much I can do with knowledge of this error constant. So if someone's giving me this error constant, implicitly the person is also telling me that, look, it's closed loop stable. So now using this error constant, you have to judge the performance metric of a system, right? So that's the first information I can draw, that it's at least closed loop stable. What's the second information the person is giving me? Look at this table here. So if I'm giving you Kp, doesn't it also mean that I've been using a step input, right? So I immediately know, depending on the error constant that the person is giving me, what type of test signal is of our interest. right. So if someone is giving me Ka, for instance, the acceleration constant, it means that the person is interested in the system's response to a parabolic input. If someone is giving me the velocity constant, it means the person is interested in applying a ramp input, right. If someone is giving me position constant, it means the person is interested in a step input and its response, right. So therefore, that is the second thing we can deduce. So it's like a detective story. You have one clue, and from that you deduce logically what else could be inferred about it. So first thing is, of course, if it has to be applicable, then it must be closed loop stable. So that is one thing probably the person is implicitly telling me. Second thing is, obviously, and this is obvious, no doubt about this, that I immediately have information about what type of test signal the person has used to obtain the value of this Ka. The third thing, if it is finite and non-zero, again look at this table. If it is finite and non-zero, right, then it's a constant. Then it's either a step with a type 0, a ramp with a type 1, or a parabola with a type 2. Now once I have already inferred what type of input the person is interested in from the knowledge of the fact that whether he has given me a Ka or a Kv or a Kp, the second thing is obvious. If it's a constant value that the person has given me, then he or she has probably given me also the type of the system, okay. So from this information I can also infer about what is the type of the system, alright. So immediately from something as simple as just a number, someone tells you Ka is equal to 25, you can immediately infer so many things, right. What is the final thing, which is of course very obvious, it's a kind of a reciprocal relationship. So if someone tells me Kp is a constant, then immediately I can evaluate this error. It's a one-to-one mapping, right. Immediately as soon as I have the value of Kp, I know the value of the error, which is again say E infinity, right. So similarly, if someone tells me Kv, I just take its reciprocal and I know what E infinity is, right, it's the reciprocal, no. So therefore, apart from these three bits of information, I can also evaluate E infinity, okay. So all these 4 bits of information, with just that one simple number, these 4 bits of information are straight away made available to me, okay. So that is why this is an important piece in the puzzle. This number, even though it might seem like a petty insignificant sort of a number, but it actually does tell us quite a lot in fact, okay. So finally, before we close this module, I would like to give you an example of a system where not only are we going to do this steady state analysis, the steady state error analysis, well maybe not, maybe I will not do it, I will leave it to you as an exercise, but also you will see a lot of useful application of this block diagram reduction technique, and which is the reason why we have clubbed these two things together, this block diagram reduction with this study of this steady state error, because these two are very correlated. You see, as I said, in order to study this steady state error, you have to always bring it down to a certain pliable form, which is the unity feedback form, unity feedback configuration, right. So therefore these go hand in hand. Just to motivate that, let me give you an example of something called a Smith predictor. So typically a Smith predictor is used to control systems that have time delays. So then the GS will be something that looks like e to the minus st times some g bar s, where notice that g bar s is a rational function of s, okay. So this is the plant. So suppose the plant or the system is given by this. So this term comes in due to time delay. Now notice that such systems are very difficult to control, not just in reality, in practice, but also if you, for instance, if you naively put this GS, yeah, and try to put it in a closed loop, let's say, with a controller, all right. Suppose you have this R of S and something like this, right, and this is your Y of S. So if you want to obtain the transfer function from Rs to Ys, you will see that Ys upon Rs is obviously given by GC upon 1 plus GC. But now notice, but because this G is not a rational function, but rather this G bar is a rational function, which is accompanied by this e to the minus st term, right, which is a complicated sort of a term. So therefore, how do you obtain closed loop poles? It's a complicated question, right? In the earlier case we saw that solve for 1 plus GC is equal to 0. Okay, that same thing still holds, but remember that when G and C are both rational functions, then eventually this leads to a polynomial, the solution of a polynomial. But now for time delay systems such as this, yeah, let us call this equation double star. This is a transcendental equation, yeah, with infinite number of solutions. Now how many such poles are you going to check? How many such solutions are you going to check? If there are infinite roots, with the polynomial we know that over the complex field, a polynomial with real coefficients over the complex field, over the complex numbers, set of complex numbers, it has basically as many poles or as many roots, rather the roots of a polynomial are as many as the degree of the polynomial. Now that you have this e to the minus st appearing with it, this becomes a very complicated question to answer. In fact, we haven't yet seen even how to talk about the stability of a system. We will do that shortly when we do Routh-Hurwitz criteria, but you can immediately imagine that this is a much more difficult problem than dealing with just rational transfer functions. So in order to control such systems, this naive technique such as this will not work. Instead what people use is what I have already named here, or what I have already introduced here by name, is this Smith predictor. So what is this clever idea behind a Smith predictor? Suppose you have this plant which is given by G bar e to the minus st, where G bar is rational function of S. Alright, so this is something I cannot do anything about, this is the plant there, right. And suppose there is a load disturbance here, there is an output here, okay, this is nothing you can do about, okay, there is nothing you can do about this, this is always going to come accompanied with the plant, some source of a load disturbance injected with this. Now given that this is the setup, as we have seen, it is a bad idea to simply close the loop around this with a possible controller here, because then you will ultimately be led to solving these transcendental equations which we absolutely want to avoid to the extent possible. So then what do you do? What then people do is, we try to get a good enough model, yeah, we try to estimate, right. So we try to estimate the parameters of this plant, and we try to say G bar can be approximated by a transfer function Gm. Now remember, a controller that we are going to implement is going to be just a piece of code, it is going to be a software, okay. So do not think that just because if this plant is a bottling plant of maybe some soft drinks company, in order to have a model of this you also have to build another replica of that bottling plant. No, the actual plant is basically the hardware, whereas your model that you have built could be just a piece of code which is going to do the same thing to the input. So given an input, there is a certain output that is derived out of the actual plant containing the hardware, okay. But when you feed that same sort of an input to maybe a model of the plant, then you can compute what the output is going to be using a computer, if your software is good enough, okay. That is what a model is supposed to do. So model is not just a hardware model, okay. When we talk about models here, we talk about softwares, we talk about pieces of code, just like the controller itself is a code, it is a piece of code, right. So that's why this is a simpler task, remember that. We are not talking about those complicated contraptions that we spoke about in the introductory lecture, let us say as in Hero's Temple or things like that, or even Watt's engine, okay. These are not hardware implementations or hardware pieces, okay. So these are just some softwares, that is why life has become a lot easier these days, right. Okay. So given that that is the situation, what then do we do? So here is what O.J. Smith proposed to do. This is a very old idea in the 1950s, if I am not mistaken. Okay. So in the 1950s, O.J. Smith introduced this idea wherein he said that, well, instead of just naively closing this loop around it, let us have a model of this plant. Okay. And suppose now, if Gm is a good enough model of this G bar, the better the model is, the better the matching between the actual plant and the software model that you've built. Okay. Of course, in Smith's days, they probably didn't have such sophisticated computer softwares, but still this idea has stood the test of time. So here is what you do. Now remember, in the actual plant, this time delay comes merged together with the plant. You cannot isolate them. But now when you are using a piece of code wherein you have isolated this delay free part of the plant, which is G bar, then you can also write a code about to depict that, right? So let me in the actual plant, although it cannot be isolated, in the code it can be isolated. So that's Gm put in here, all right, and I can tap in. So I can have a tap in point here, okay, a pick off point here, and I can then write a code for a pure delay ST bar, and T bar is an estimate of T. Okay. So based on how well I know this model, how well I have understood this model, how accurately I have captured its behavior, I will be able to get a model for the delay free part of this, which is G bar, and also for the pure time delay, which is e to the minus st. And then what I do is, I have a summer here wherein I take the difference between the two. So whatever, remember, the common signal is coming into this. Of course, there is some load disturbance which I cannot measure, right? That is why I have not added this to my code here, because this is something that is coming extraneous to the system. I have no control over this. Okay. So therefore, the best I can do is whatever inputs coming in through here into the actual plant, I am giving the same input to the plant model here, and I am comparing them. So I am taking the difference of the two. And then, because I can now in my code at least isolate this, yeah, remember this part is part of the model and therefore it is a part of the code. So therefore, I take a tap out of this or a pick off point from out of this. So this is like going to as if predict. Why is it a predictor? Because remember, my actual plant does not allow me to isolate this G bar and e to the minus st, but if I have modeled this actual plant with the time delay well enough, then I have a very good model or very good idea of what Gm is like, or what e to the minus st hat is like, or T bar is like, right. So therefore, even though I cannot tap into this actual plant to get the response due to the delay free part, in the model I can actually get a tap out of this delay free part and feed it back. Normally this signal, this tap in point is not available in the actual plant. So what the next best thing I do is, I get this tap in point out of a model of the plant, okay, because I can do as I please with the model. So that is one of the pivotal central ideas behind this. Okay. Once I have done this, now I have access to the delay free part. So intuitively, I ought to be able to do much better. Okay. So now, sorry, I probably missed that. Yeah. So now I can, now that I have access to this delay free part here, now this is what I call my controller, CS, this block. Okay. So now I pass this signal here. And what do I do with this difference? Remember, I also want to kill off this difference, isn't it? So therefore, what I do here is, suppose this is my reference input, reference signal, right? So here's what I do. Okay. So that is the complete structure of the Smith predictor, right, where we have the actual plant, we have a model. So remember, this is something that we are designing by a piece of code, this is something we are designing by a piece of code, and this is also something we are designing by a piece of code. Only thing that over these we do not have any control. Whatever is best for the plant, whatever is the best approximation of the plant, we just pick those parameters here in these two. But this controller is in our hands. We can make this a P, PI or PID controller as we discussed in the previous lecture, right. So now that we are faced with this, what is the transfer function GS is equal to ys over rs, that is what we want to evaluate, and then we also want to evaluate gls, which is basically ys over ls. Okay. So, what we want to do is then we want to find out what will be these two transfer functions. We want this transfer function to tend to unity, yeah, as s tends to, yeah, as you know, for maybe let us say a step input. So, we want ys is equal to gs rs, okay. We want limit s tending to 0, which is basically nothing but limit s tending to 0 to go to unity. Suppose rs is equal to 1 by s, okay, for a step input. Typically people are concerned with step inputs here. So, then of course, you can cancel out this rs and s, because rs is 1 by s and this is s, right. So, you can just cancel it out. So, you basically want this, alright. Let me not call it gs because I have already named gs as this. So, this is let us say grs, okay, yeah, that is better. So, this is grs. So, we want this grs, this part to go to unity, and on the other hand, and limit s tending to 0 s ls gls to go to 0. Why? Now, typically we also consider a constant load disturbance. Suppose ls is equal to 1 by s, okay. So, typically if it is a constant load disturbance, then we want this to be able to reject it. The effect of this load disturbance should not be felt in the long run, yeah. So, therefore, what we want is this transfer function to go to 0, and based on these two goals, design CS to meet these requirements. Now, you see immediately the first thing that you are faced with when doing this is, of course, convert this to a unity feedback equivalent. You already have that unity feedback as a matter of fact. So, for instance, if you just focus on this, alright, if you just focus on this part, yeah, remember because of the sign reversal here, this is basically a negative unity feedback, even though there is a plus sign here, but because there is already this negative sign here, so this is tantamount to a negative gain, okay. So, what you then need to do is to look at the equivalent transfer function of this part, okay. And again I leave it to you as an exercise, you know, just by moving the pick off points and the summers and doing some of those, playing around with those parallel equivalents and all. So, you see for instance here, yeah, you see that there is this, this is a parallel path, right. So, for example, there are these simple modifications that you can make, and you will see that I leave it to you as an exercise to check that this is nothing but tantamount to the following system. What is it? So, you will have this, you will have this, right, and you will have an inner structure such as this with a minus sign, and then the goal is that I want to bring out everything that I have got to design on one side and isolate the plant, yeah. So, that gives a very transparent picture of which part I am allowed to or required to play around with. So, this is of course the plant g bar e to the minus st, yeah, this is y, this is r. So, this is a nice place to flex your block diagram reduction muscles, okay. So, if you practice those problems well enough, you should be able to see how this block diagram which I have drawn here in this figure is actually equivalent to the one that I am now drawing, okay. So, this, and you will see that now of course I have missed this load disturbance here, let me quickly draw that here, yeah. So, this is an LS, so this is a plus, right, okay. So, now you see that this is going to be equivalent to the following diagram. What is this? So, this is nothing but Gm e to the minus S t bar, okay. Yeah. So now you see if you manage to do your block diagram reductions suitably, you will immediately be able to see that this is what that block diagram is equivalent to. Why this is preferable over the other? Because here I can as if focus my attention on this part and say that this is my actual controller. Although it looks like the CS is the controller, but the overall controller to be designed is sitting pretty with inside this dashed box that I have drawn in red, okay. So remember, this GM is depending on how well I have modeled G bar, this T bar is depending on how well I have modeled T, okay. So this is the plant, okay. So this part is kind of fixed by my estimation capabilities, and this part is where I choose whether I am designing a P or a PI or a PID controller, right. So that is basically the goal. And now once I have done this, you will immediately notice that if GM is equal to G bar and T bar is equal to T, now it becomes very straightforward. Why? Because this part I know is in a standard feedback configuration, so this is basically nothing but C upon 1 plus C GM e to the minus, okay, let me get rid of the GM, just call it G bar, because now I am using the fact that they are, it is as if I have accurately modeled. Model is accurate. So it is C e to the power minus st. So this is now my overall controller, right. And now I can connect this as if this is the L, LS, alright. This is my G bar e to the minus st, and then I have this overall RS, this negative feedback going in here, alright. So now that we have this figure, this is a simplification of this subject to these assumptions. Now it is very easy. If I just want to find out the transfer function from R to Y, all that I need to do is to take the cascade combination of these two, right. Okay, I should write G bar here, right, yeah. So the cascade combination of these two and take this, alright. Now you see, interestingly, what happens is Y by R is given by, again for brevity's sake I will arbitrarily be dropping this S argument whenever I find it convenient according to the space available. So of course you are not encouraged to do that for an exam purpose, but I hope you get the idea behind this, okay. I am just dropping this argument in S for all purposes of understanding this concept. It is not really going to be hampered, correct. So I missed this 1 minus, you see that will happen because there is this GM, something going straight through GM here, right, and then something going through both GM and e to the minus st. So that is basically something, the same signal times GM going back, and then the same signal times GM times e to the minus st also going back, right, and because they have opposite signs here, plus and minus, so there is a difference. So I probably missed that. So yeah, that is what comes of skipping steps, I suppose. So I hope you will not be making the same mistake when you are doing the block diagram reduction. So then how are we going to simplify this? Again, let me just write that. So it is Y by R is given by C G bar e to the minus st bar upon 1 plus C G bar into 1 minus e to the minus st bar, yeah, I suppose that is what it is, true, divided by 1 plus C G bar e to the minus st bar upon 1 plus C G bar 1 minus e to the minus st bar, yeah, subject to the modeling accuracy we have assumed that GM is equal to G bar, as I said. Therefore we have C G bar e to the minus st bar, that is going to remain on the numerator. Remember, this denominator is going to cancel out because it is common, and what you will then be left with is 1 plus C G bar 1 minus e to the minus st bar plus C G bar e to the minus st bar. Now look at the beauty of this. In one shot, not only have you, in practice it's easy to see that why this should give a better performance, because we have been able to tap into this point. Now tapping into this point has not only allowed us to get a prediction of what would happen, because remember, at any instant of time what this plant is giving me is a delayed version, but if I am able to tap into this, it's as if I know in advance, even before the plant has actually spat out that output, I know in advance, I have an idea about what is to come out of the plant after some time. So that is why it is kind of a prediction, and that prediction allows me to do better. Okay, so that is the intuition behind this. But in the process, what also happens is, now notice that if you want to get this closed loop transfer function of this system with the Smith predictor, you will get something like C G bar only. Why? Because this term and this term cancel out. So now the poles are given by 1 plus C G bar is equal to 0, right, which is not a transcendental equation, because remember, G bar is a rational transfer function, right. So therefore you see that now by using the Smith predictor, not only have you been able to get an idea about what is to come out of the plant in some time, right, you have tapped into the interior of the plant in some sense, but also you have gotten rid of this problem or bypass this problem of having to address these transcendental equations while solving for closed loop poles. Yeah, so that's an attractive feature of the Smith predictor. Okay, so I hope that you've learned something interesting with this, and the tools we have used are very simple, nothing other than just block diagram, simple old fashioned block diagram reduction. Okay, but remember, the time delay systems are pretty complicated class of systems, and to be able to do something like a Smith predictor is pretty commendable. Okay, and the fact that it was done in the 1950s makes it all the more attractive. All right, now having seen this, the other goal, remember, is to reject this load disturbance. So if you want to find out the transfer function between this, recall this diagram. What is the forward path transfer function? It is G bar e to the minus st. So what is then y upon L? Okay, so what is this transfer function going to be? Yeah, so we suppose we consider Ls is equal to 1 by s, and can this Ls be rejected if G is type 1? Okay, so if it has an integral mode, that is an important and interesting question. Okay, so I've just written that down. Let's try and take a look at this. A closer look, inspection of this transfer function should reveal something. You can take that as an exercise to verify this. Okay, and I'll tell you later why that is an important question. Okay, so let's take a look at this. So if I look at it from L to Y, what is in the forward path? G bar e to the minus st. So let me just write that down here. So it's G bar e to the minus st. All right. What is in the feedback path? This, with a negative feedback, of course. So what can I write then? So in the denominator I will write once again the same thing, 1 plus C G bar e to the minus st. Of course, if I write t or t bar, it does not make a difference because they are one and the same. Yeah, and then I write 1 plus C G bar into 1 minus e to the minus st. Right? What does this lead to? Now you see, unlike in the earlier case where this common denominator cancelled out from y to r, here we do not have anything in the denominator for y by L, isn't it? So this gives us a rather complicated looking sort of a transfer function, but nevertheless we have to write this G bar e to the minus st times 1 plus C G bar into 1 minus e to the minus st. Okay, that is what comes in the numerator. This does not get cancelled out, unfortunately, this time. Yeah, and then in the denominator you have, of course, the usual term cancelling out. So you will still come up with 1 plus C G bar. So one problem is still resolved, that is that you do not have to solve for a transcendental equation in order to get the poles of this system. But now if you want to find out if this transfer function is good enough to reject this load disturbance, you will have to then apply final value theorem, with Ls is equal to 1 by S, right, and apply S times this. So S and 1 by S, this cancel out. So you will have to apply limit S tending to 0 here. And now because you are considering that this transfer function is going to be of type 1 type, so therefore this is going to be written as some g, yeah, so this is going to be written as in the form where this g bar 0 is defined, no, it is constant, yeah, right. So now, sorry, what was it? Yeah, so this was g bar. So now if it has integral mode, yeah, so if it is defined then it's fine, we can all go about it. Now if suppose the question is that if this g bar is of type 1, then this is not defined anymore, no, right. So if g bar is of type 1, then this is not defined. So then you will have to apply the limit as S tends to 0, and you will have to use this, let me just write it as a side note. So you 1 minus e to the minus S upon S limit S tending to 0 is equal to, yeah, t. In general, if this t was unity, then this will be unity, okay. This is just one of those early limits you might have learned in high school, right, yeah. So you will have to make use of this, right, because you remember this 1 by S will be extracted out of here. And then you will notice something very interesting, something very curious. You will see that if you have a constant load disturbance and if you have a type 1 plant, then although the Smith predictor allows you to track the reference signal, that is this goes to unity as limit S tends to 0 with 1 by S times S, all of this, but this does not go to 0, so it is incapable of rejecting a load disturbance. And in fact, well until the last 20-25 years, a solution to this was not known. So what I am trying to impress upon you is that, see, even though this appears like very trivial sort of undergraduate level, very basic level of control theory, right, but at least 20-25 years ago, Smith predictor, as I told you, was discovered in the 1950s, but despite that, despite 70 years having passed, I mean maybe 50 years, around 2000, it was only around that time that people came up with some strategies or some modifications of the Smith predictor which would allow you to simultaneously not just track the reference but also reject the load disturbance. So even things that emerge from these undergraduate lectures or discussions might one day, you know, lead you to discover something interesting, who knows, yeah. Unless you think about a problem, you don't know what you want to solve, right. So that is a refreshing thought, and I hope that that's something interesting to carry forward, something encouraging, yeah, that should also encourage you to sort of read up and understand the concepts of this classical control topics, right. Okay. Before we close this module on these structures, these special structures, or you know, this in general, this steady state error, okay, here's another quick example that I would like to refer to before we bring this discussion to a close. So that is, for example, now suppose you have, okay, let me take this example of this plant here, yeah, suppose you have this plant here, which is this, there's this reference input, all right, there's this, so this is an actuating error, by the way, not the actual error, okay, because there's going to be some non-unity feedback. So you already know how to sort of play around with this in order to get it or massage it into a unity feedback format, okay. Suppose now there is this load disturbance here and there is this plant here, all right. So this is Y, yeah, so this is the plant, I don't want to make a mistake with this. So you take this as an exercise to see that the error, okay, remember not the actuating error but the error, okay. So take this as an exercise, if you are able to do this, again this will give you good enough practice, okay. So you will see that 1 minus C G upon 1 plus C G H times R Rs, again these are also all arguments in S, I have dropped them for brevity, minus G upon 1 plus Cgh times D, D of S, or rather L of S. So, I call it the load disturbance, so it is L of S. Okay. So, you show first, so show that this is the case, and then further I tell you, suppose the plant GS is of type 0, okay. Suppose the plant GS is of type 0 and HS, which is sitting in the measurement loop, okay. So, this is basically maybe some measuring device which is allowing you to measure this Y and then feed it back for comparison purposes, okay, and HS is also type 0. Then in order to, okay, so now by now it is implicit, so I am not going to mention, as an intelligent control engineer, by now if you followed these lectures you would know what should be the goal of this. The goal should be to ensure that this ES goes to 0. Now if ES has to go to 0, then notice that this has to go to 0 and this also has to go to 0, okay, as S tends to 0, okay. So you basically want to ensure that maybe Rs is equal to a step, Ls is also equal to a step, that is an information given, mostly we are concerned with step responses. So what you then basically have to do is, because remember if Rs is 1 by S, then S times 1 by S, that 1 S times comes because of the application of the final value theorem, right, and 1 by S comes because of Rs. Again similarly for Ls, 1 by S comes because of Ls, because it is a constant load disturbance, and S times that comes because of the final value theorem, as we have already seen. So therefore what you then need to do is limit S tend to 0, you have to tend these, both of these terms go to 0. So then what should be the type of CS? Notice this controller is something that you are going to design. So this is a controller. So as a control systems engineer who is tasked with designing a controller that at least, if not anything else, forget about those requirements of rise time, peak time, percentage overshoot and everything. The first thing that you have to decide is, because you want to address this tracking problem, you want to have 0 steady state error. So in order to have 0 steady state error, the first thing you have to decide is what should be the type of CS. What will help you there? Getting a transfer function such as this from Rs to Es and Ls to Es. Okay. Remember ES and EAS are not the same. So notice this and this not the same. Why? Because this ES is to be obtained once you have put it in the unity feedback configuration. So I have repeated this so many times, I hope that it is now ingrained in your memory, right. So the point is, now the question you have to answer as a control systems engineer is, what should be the type of C? Given that G and H are of type 0, what should be the type of C in order to ensure that this transfer function or this suitable design of this controller will lead to 0 steady state error, okay. So that is the question I want to leave you with. The next topic, probably we will start discussing about this in the next lecture onwards. The next topic of our interest would be that of stability. So throughout the discussion on this steady state error, I have said this countless number of times, I suppose, that we will always assume that the system is closed loop stable. But as I said or remarked in the previous lecture also, as a control systems engineer you cannot get away by saying that, especially for someone who has completed a course on control systems. You should be able to determine by yourself as to whether a given system in its closed loop configuration is actually closed loop stable or not. So in order to do that, we have to basically keep track of the number of closed loop poles that are in the RHP and the number of closed loop poles that are in the LHP, left half of the complex plane and the right half of the complex plane. If all my closed loop poles are on the left half of the complex plane, then my system is stable, and such polynomials are called Hurwitz, and that is for a reason, because it is this Routh-Hurwitz criteria that we will study next, and these two gentlemen, Routh and Hurwitz, basically gave us this method to discern as to whether a given polynomial has all of its roots on the strictly open left half plane. What I mean by open is you are excluding the boundary. What is the boundary between left half and right half of the complex plane? It is the imaginary axis. So if you want all our poles in the strict left half of the complex plane, it means we are also excluding the imaginary axis, where, remember, I said that if your poles lie there, the system is marginally stable provided there aren't any repeated poles, but that was with respect to something called Bibo stable. Alright, so we said that now we are concerned with a polynomial being Hurwitz or not. For that we even exclude that imaginary axis. Okay, so we will come up with this strategy to find out that given a polynomial, whether all of its roots are in the left half plane or whether there is even one fellow that is on the right half plane. Remember, for stability you need everyone to be on the left half plane. For instability, even one fellow, one of those poles being on the right half plane suffices to spoil your party. Okay, but we will see that this Routh-Hurwitz array will do much more. Short of giving us the exact roots, which is of course a difficult computation to make for higher degree polynomials in general. In fact, beyond 4th degree polynomials, you will not have any foolproof method that will give you a closed form expression for the roots. You will only have to resort to numerical methods, right. So short of giving us the exact roots, Routh-Hurwitz does a lot. It tells us exactly the distribution of the roots. So how many are on the left half plane, how many are on the right half plane, how many are on the imaginary axis. We can actually get a complete picture of this, okay. And the good thing about it is something you can do using hand computation. You will not need even a calculator in most cases. Of course, if it is a very big polynomial, let us say a 100th degree polynomial, then it is rather inefficient to do it by hand, but probably, who knows, if you are just cast away on an island and you have just a piece of twig on the sea beach, you might be able to write down that 100th degree polynomial on the sea beach and then work your way around and keep count, okay. That is just a poor joke, I understand, but the point is that this simplifies matters, and you have to remember that when these two gentlemen, when they came up with this method, those are not the days of computers. So it was a great achievement in those days, okay. Remember that engine I spoke about, Watt's engine, right. So the stability of that Watt's engine wasn't provable until this gentleman Routh derived this condition, okay, for stability. Of course, Routh used a lot of very high sophisticated mathematics. He used tomb sequences to prove the results. We will not get into that. Thankfully, we live in times when a lot of people have researched into these topics, and we will see that some very simple techniques make the proof, or at least give us a glimpse into the proof of this Routh-Hurwitz criteria, and at least suffice to convince us as to why these results are correct and valid, right. So we will see some sort of an idea, we will get an idea about why these results are correct, and we will see, we will delve into this question of stability. The first such tool is going to be Routh-Hurwitz criteria, okay. So all in good time, all of that is going to be in next class. So I hope that before you attend the next lecture, you have at least attempted these questions, okay. You at least attempt to convince yourself that indeed you are able to discern what sort of a controller will allow you to meet both these objectives, that is, get a zero steady state error in the face of a step response, reference input, sorry, and a constant load disturbance. So you are able to reject the constant load disturbance and you are able to track the reference signal, okay. These are important ideas that go into the making of a control systems designer, okay. So the next topic, as I said, we will have is Routh-Hurwitz criteria, and we will start that discussion from the next lecture onwards. I hope you have enjoyed the lectures up until this point. Thank you very much.